In this video, we'll talk about linear regression and when you might use it to model the relationship between two numerical variables. So, linear regression models a particular kind of relationship between variables. Just like with correlation, we want to use this to model linear relationships. So essentially, we model the relationship between some explanatory variable x and some response variable y simply by using a straight line. So y is equal to beta 0 plus beta 1 x plus some additional error term epsilon. We use beta 0 to stand for the y-intercept in this model, and we use beta 1 to represent the slope. So based on our data, we'll take our theoretical model and we will fit it to the data set. So we'll come up with our best estimate of the linear regression model like this. So our best estimate is that y hat being our predicted value of the response variable, that's equal to our predicted value of the slope, our predicted value of the y-intercept, beta 0, plus our predicted value for the slope, beta 1, times x. Now the two parameters of this model, beta 0 and beta 1, have very special interpretations. So beta 0, or the predicted y-intercept, this is the value of the response variable that we would predict when the explanatory variable x is equal to 0. Then beta hat 1 represents the estimated slope, or the estimated change, if you will. So what happens to our response variable y when we increase our explanatory variable x by 1 unit. So for an example, we'll take a look at a study that was done to measure empathy in the human brain. So here's how this study worked. Researchers recruited 16 heterosexual couples in their mid-20s who were married or had been dating for at least 2 years. So they recruited serious couples to participate in this experiment. As they watched, or as the female watched her male partner's hand being zapped with an electrode, they measured the activity that went on in her parts of the brain that would respond to pain. So the idea was, is she having sympathetic feelings of pain as her partner is being zapped? They measured this brain activity as a fraction of the activity observed when the woman was being zapped with the electrode. So both partners experienced this. An activity score of, say, 0.5 would indicate that the woman felt half the pain watching as she did when she actually experienced it. Now, they wanted to see if they could predict how the women would respond just based on a psychological test measuring empathy. So do people with higher empathy scores actually have higher chemical and physical signs of empathy? So let's start by writing the response in the explanatory variable and the linear model. So our response variable is the reaction to the partner's pain. We think that we'll be able to explain any changes in that based on the empathy score. So that is our x. Now we can write this model two ways. I know some students will prefer writing it in terms of y's and x. So y is equal to beta 0 plus beta 1 times x. If you prefer to write it in words instead of symbols, that's okay too. So the partner's brain activity is a linear function of their score on the empathy assessment. Now, before we actually fit this linear model, we should check to make sure that it's appropriate for the data at hand. So we'll look at the first 6 observations using the head function in R. We can see that empathy is a numerical variable, which is good, and brain activity is a numerical variable. So both variables are of the appropriate type for linear regression. Looking at the correlations here, we want to see some evidence of a linear relationship between brain activity and empathy score. So we find a correlation of roughly half, roughly 0.5. So there is definitely some sort of a linear relationship, or some sort of a relationship, between these two variables. Now, correlation doesn't guarantee that it's going to be a linear relationship, so let's look at a scatter plot of the data also. So this geom smooth function that I've highlighted, this is what is adding the linear model. So method equals LM. SE stands for standard errors, so we're not drawing any errors around this bar by writing SE equals false. So we just want to see what the linear model would look like. So here it is. In general, as empathy scores on the x-axis are increasing, so is brain activity. One thing to be cautious about with this data, however, is that we have an outlier, someone with a much higher empathy score or a much higher x than the rest of the observation. So this outlier may be of concern later on. So let's start by just writing the fitted linear regression model. In R, the function to actually calculate a linear regression model is LM. LM stands for linear model. So we'll say that our y variable, brain activity, depends. Remember, you can read this tilde as depends or is a function of. So brain activity depends on empathy. The data set is called the brain empathy data set. So that's how we'll calculate this model. We get back two estimated coefficients. So we get back an estimated beta 0 in this intercept column, and we get back an estimated beta 1 in this empathy column. So our fitted regression model is this. Y hat I is equal to negative 0.007254 plus 0.006938. Now, one thing to point out is that just because this intercept is a small value and this empathy is a small value, doesn't mean that there is not a linear relationship. The values that we get for the intercept and the slope are going to depend on the units of the actual data. So we can predict or estimate y hat for any value of x using the model that we've just calculated. So we can plug x's directly into this formula to predict the response variable y. So let's pretend that we'll have a new couple who's going to come participate in this experiment. The female partner takes the empathy assessment. She scores an 82 on it. We'd like to predict her brain response to the shocks that will be given to her male partner. So to get our prediction, we'll take that 82 and plug it into our linear model for x. So calculating that out, we get a prediction of about 0.56. In other words, we think she'll feel about 56% of the pain that she actually felt when experiencing these shocks herself. Now, sometimes we'll overestimate, sometimes we'll underestimate. That difference, or how far we're off, we call the residuals. So the residuals are just the difference between the predicted value and the observed value in a regression model. We can also think of these as the errors, so how far off we actually are. So this subject 2, the second individual in our study, has an empathy assessment score of 53 and a brain response score of 0.392. So what we'd like to do is then predict her brain response and calculate the residual. So let's do the prediction first. Our prediction is that y hat is equal to negative 0.007 plus 0.0069 times her actual empathy assessment score of 53, and we get a predicted brain response of 0.36. Our predicted value is a little bit less than what actually happened, so our residual will be negative. If we take our predicted value y hat minus the actual, we get negative 0.03. So this negative value here indicates that we have underestimated. Whereas if this residual had been positive, that would tell me that we've overestimated. So let's take a look at another example. So we'll take a look at subject 3, who is actually quite the outlier in this experiment. Subject 3 has an empathy assessment score of 41 and a brain response of only 0.005. So you can calculate her predicted value and residual on your own. You should get these answers here. Notice how large this residual actually is. For subject 3, we've really overestimated how she would react. Now, you may be wondering where we get this linear regression model. Typically, we choose these using a technique called least squares regression. The basic idea of least squares regression is that we would like to choose the fitted line to satisfy two criteria. First, we'll make sure that the residuals, or those error terms, sum to 0. Some residuals will be negative, some will be positive. We want them to average out to be 0. Second condition is that the sum of the squared residuals should be minimized. So we want to make sure that we have the smallest possible squared residuals. If you're a visual learner, there's a really good explanation at this website, setosa.io. I strongly recommend that you guys check this out and play around a little bit with how these regression lines are found. So there are some conditions for the linear regression model, and you can think of these conditions as being the line conditions. There's a nice little acronym there for you. So the first condition, the L condition, is that x and y must have a linear relationship. We wouldn't want to use a linear model to predict a curved relationship. Second condition is that the individual observations, and therefore the residuals themselves, must be independent. They should not be related to one another. Third assumption, the residuals must be normally distributed, so we want them to not only average out to 0, but we want them to be normally distributed. So most of the residuals should be small, should be close to 0. A few will be on the outside of that bell curve. And then finally, we want those errors to have a constant variance. We don't want the variability of the errors to be increasing or decreasing. We'd like it to stay the same. So let's take a look at the linear model against this brain empathy data. So there is a linear trend here. It looks like most of the residuals are going to be fairly close to the line. Most of the points themselves are fairly close to the line. Again, we might be a bit concerned with this outlier in the data. We can get a bit more information about this linear regression model if we save it first in a new R object. So my model output is now saved as a model, and then apply a function called summary. So this summary, just like the analysis of variance model, will give us a little bit more information. Now there's a lot going on in this summary table, and I want to break down some of the most important pieces. The first table that I like to look at here are the residuals. So we'd like to know whether or not the residuals are normally distributed with mean 0. If they are, the median or the center of that distribution should be near 0. So we want to check to see that this median is near 0. Normal distributions are also symmetric. So the first quartile and the third quartile should be roughly the same in terms of the absolute value. So with this data set, things are looking pretty good. If we go down to the coefficient table, we get back the estimates. So this estimate is the exact same as what we saw with the previous output. We also get a little more information. We get a standard error of our estimate. We get a t-value for our estimate, and we get a p-value. So it looks like we're doing some sort of hypothesis test on our model as well. This hypothesis test is what's going to let us know if our model is, quote, significant. So if there's a strong relationship between the variables. Specifically, what we're going to look at is right here, this p-value for the explanatory variable, for the empathy. If that is sufficiently small, then there's a strong relationship between the two variables. Essentially, we're actually doing two hypothesis tests. We're doing one for the intercept, one for the slope. The intercept one doesn't matter as much. So our first null hypothesis, the one for the intercept, is actually that the intercept is equal to 0. We're testing that against the alternative. This should read not equal to 0. So beta 0 is either equal to 0 or not. If the y-intercept is equal to 0, that doesn't really tell us anything about whether or not x and y are related. It just tells us where to stick that predicted value when x is equal to 0. However, same typo, this should be a not equal to 0. However, if the slope is significantly different from 0, that does tell us that x and y are related. That tells us that there is a change in y that's related to a change in x. Whereas a line with slope 0 is just simply flat. There's no relationship. So let's look at how we might evaluate these model conditions. One thing that we can do is use a scatter plot of the residuals plotted against the predicted values or the fitted line to tell whether or not we have a constant variance and whether the independent residuals or whether the residuals are themselves independent. Here's what you want to see in this. You want to see random variation above and below 0, a gray dotted line essentially with no patterns or runs. To evaluate these, we'll use the function plot, so we'll just make a plot of our model. This code actually produces 4 models or 4 plots. We only care about the first 2, so that's all we'll be using. So here's what that residual versus fitted line plot actually looks like. There's a gray dotted line at 0. You want to see all of the points sort of drop along that line. Here we're not too bad. There might be a problem though with constant variance. Now it's difficult to tell because we don't have a lot of data, but this plot is getting wider and then gets a bit narrower. So this isn't exactly what we would want to see. On your homework assignment for regression, you'll see a lot of examples with some residual plots next to the data that they came from, which should help solidify how to interpret these things. The second type of plot that we'll use is a normal QQ plot. We can use these to see whether or not residuals are normally distributed. This is the second plot that gets produced with this plot function. So here's what our normal QQ plot looks like. Thinking back to our section on the normal distribution, we want plots to fall along that dotted diagonal line. And it looks like they do. I'm not really seeing any major problems with that normal QQ plot. So one thing that we want to look at in the data, or something that can cause problems in linear regression, are outliers. So outliers are data points that are pretty far from the pattern of the rest of the data. One thing that we might use to help us decide whether or not a point is truly an outlier is a standardized residual. So we might take the residual for each of our observations, or the error terms E, subtract the mean of the error terms, and then divide that by the standard deviation. Essentially, calculate a z-score. So standardized residuals with absolute value greater than 2 are unusual. Absolute value greater than 3, definitely going to be considered an outlier. We might also look for influential outliers. So influential outliers are ones that are going to tilt the regression line. So either tilt the regression line toward that point or perhaps push it away from another type of line. In the residual plots, these relatively large outliers are often identified with their observation numbers. So for example, observations 5, 7, and 10 are highlighted because they have the largest standardized residuals. Those are definitely points that we might consider when we're looking for outliers. Now, if we want to take a look at where those points actually do fall in our data set, here's how we can accomplish this. I can use a label plot geometry to add a label to my plot. And the label is just going to be the row names for brain empathy. So row 1, row 2, row 3, row 4. That's going to indicate the subject numbers. So subjects 5 and 7 are down here. They have the largest negative residuals. However, they're right in line with the trend, so I'm not worried about those. Observation 10 has the largest positive residual, still right in line with the trend, so I'm not that worried about observation 10 either. The one I am worried about is 6. What would maybe happen if we removed observation 16 from the model? Would that change our linear regression model? It looks like it probably would. Now, one other thing that I tend to worry about with these regression models is something called extrapolation. So extrapolation can be pretty dangerous when you're using a model. Extrapolation happens when we predict beyond the range of observed data. The reason why this is a problem is because we don't have any data to tell us whether or not some pattern has held or whether or not some pattern is still true later on. So that's why this could be really dangerous. So for example, what happens if we've got a subject whose empathy score is 0? The lowest empathy score we actually observed in this data was about 20. So we're pretty far below the observed range of values. This particular person we would predict to have a brain activity score of negative 0.007. This brain activity score is negative. We can't have negative percents of some baseline activity. So we get a prediction that just doesn't make sense. It's not reasonable given the data. When we extrapolate, we're assuming that the pattern in the data will not change. And this is a really strong assumption. The best thing to do is to use our linear model in areas near the data, but not too far beyond the data. Now, the last thing that's useful for us when we're talking about our models, or a linear model in particular, is how good this linear model actually is at explaining changes in the data. So, for example, how much of the variation in our data can be explained? The value that we'll look to give us an answer is down at the very bottom of the summary output. It's something called multiple R squared. Another term for multiple R squared is the coefficient of determination. So the coefficient of determination simply is the proportion of the variation in our response variable that can be explained using the linear model. So our model looks like it's explaining about 26% of the changes in brain activity based on the empathy score. Now, there's a reason that this is called R squared, and the reason is because of a relationship between the coefficient of determination and the correlation. Specifically, if I take that correlation from the brain activity level and the empathy, so 0.508, and square it, I get the coefficient of determination. So R squared is literally just the correlation squared. So once you know one, you're able to find the other. We'll stop here for our introduction to linear regression. The last set of videos in this class, which you will see next week, will be about multiple regression. So what happens when we want to extend this model to more than one explanatory variable. Have a great day.